So this table tells you what the typical equilibrium potential is for these four very, very common ions in your body across a typical cell, okay? And they're all, you can calculate them all by plugging in these numbers into the Nernst equation, and you'll get these numbers over here, all right? And these are typical physiological concentrations, all right? So if you plug in the numbers for potassium and do the calculation, you'll find out that the equilibrium potential is minus 95 if I have a membrane that is selectively permeant to potassium only, and then the voltage across that membrane will be minus 95 when the potassium stops flowing, okay? For sodium, it is plus 60. So that means that now you'll notice sodium moves the other way, from outside to inside. So the sign changed. Instead of a negative equilibrium potential, we now have a positive equilibrium potential. And sodium flows down its gradient if the membrane is permeate to sodium only, with sodium channels only. And it will stop when you hit plus 60 millivolts. All right? Now, let's get tricky. Now I'm going to put potassium channels and sodium channels in there. And I'm going to say the permeability to that membrane to potassium and sodium is the same. What will the final voltage be? Who says minus 95? Who says plus 60? Very good. Who says halfway in between? Okay, well, that's one person who cares. It is halfway in between. Here's the reason why. This is Ohm's Law. G is the permeability, conductance, permeability. And it is the same for both ions. And if I plug in minus 17.5 for the membrane voltage and I plug in minus 95 for EK, I will get a current. All right? And if I will get a flux, current of ions. If I plug in minus 17 and plug in plus 60, I will get a current. Those currents will be equal and opposite, so that the net current is 0. And when the net current is 0, the voltage stops moving, and that will be your resting potential in that membrane. Net current is 0 at the resting potential, and you know that because the voltage is changing. If there was a current across that membrane, if I was putting more positive charge inside than positive charge going out, then my voltage would be going up. If I was taking positive charge out faster than positive charge was coming in, then I'd be making the outside positive and my membrane voltage would be going down. At rest, it's not changing, so the currents all have to add up to 0. In this case, they're equal and opposite. Okay? And that happens if you plug in the numbers and calculate the currents with Ohm's law. That happens at minus 17.5 in this case, as I defined it. Now, let's keep them permeate to potassium and sodium, but let's use realistic permeabilities. So if I'm at rest in a typical cell, I said last time that the permeabilities will equal. Well, in fact, the permeability to potassium in a resting membrane is about 50 times the permeability to sodium. So now what will the membrane voltage be? Okay? The answer is given by this equation, the Goldman-Hodgkin-Katz equation. I will not ask you to do a calculation with it. You should understand the relationships. You should understand the equation. It also appears on boards. And that is why I'm using it rather than the cord conductance equation, which is also described in your notes. All right? This, if you plug in the numbers, will give you an approximation of the resting potential in a given membrane. Let's ignore chloride for the moment. And now we have an equation where we can plug in both potassium and sodium and with the permeabilities, in this case we'll call it 1, in this case we'll call it 50, you will get a membrane voltage, okay? And I want you to notice before we move on that if I take sodium out and make this membrane only permeate to potassium, that the Goldman-Hodgkin-Katz equation reduces to the Nernst equation. P becomes 0, PNA becomes 0 if I have no open channels and the membrane is not permeate to sodium. And what I have left is the Nernst equation for potassium. Okay, so that's where this equation comes from. It's just based in the Nernst equation. It's just that we're applying it to multiple ions at once. Okay. Let's bring sodium back, do the calculation. You can confirm this if you want. The membrane voltage will be minus 80. Okay? So if you take these voltages, take minus 95 and plug it in here, and minus 80 and plug it in here, and 50 and plug it in here and do the calculation, you will get a current. If you take plus 60 and minus 80 and use 1 for GX, you will get a current, and those currents will be equal and opposite, because minus 80 is where you will get no net current across the membrane. That is where it will come to a resting voltage. All right? There is mud. For your own information, the sodium, this is a rough approximation. The reason is because the sodium-potassium ATPase accounts for about 10 millivolts. It's transporting 3 sodiums out for 2 potassiums in, so it is always making your inside a little bit more negative. And so you have to account for it because there are so many of them in a typical cell. So it'll lower that value a little bit more. Hence, in a typical muscle cell, you have minus 90, not minus 80.